Hey everyone, thanks so much for being here and for inviting me. I actually grew up in Portland, Oregon, just down south a little bit, so it's a great pleasure to be back in the Pacific Northwest. Today I'll be talking about abstraction in reinforcement learning. So it's no secret that computation has just totally transformed our world, from art to urban planning to communication to even fundamental science. The world has forever changed because of our ability to systematically solve problems with machines. However, the reason I get excited about reinforcement learning is that I believe it can help empower us even further. So typically, of course, our computers will map well-structured input to well-structured output. So in answering questions about a graph, we might take as input some data structure representing that graph and then output an answer to the question we ask, like, yes, this graph is planar. But we really lack clarity about what happens when the input is instead some arbitrarily rich observation of the world, rather than some known data structure. And similarly, the output here might not be an answer to a question, but rather a series of complex motor controls that move the computer through the world, perhaps to get a closer look at this chalkboard before answering questions about its contents. So now this is starting to sound a lot more like AI and robotics and reinforcement learning in general. So it's in this sense that I think reinforcement learning is immensely important because it can capture this notion of systems that learn to solve problems through observation and action alone. So instead of just thinking about this structure-to-structure mapping, we can study agents that are built to deal with the complexity of the world at the level of observations and behavior. And in order to bridge this gap between this complexity offered by the world and the structure expected of our computational models, that's where abstraction comes into play. So this is what gets me excited about the combination of reinforcement learning with abstraction, is this promise of a new kind of problem solving that can bridge this gap. So in this talk, I'm going to show how we can use abstraction to help RL agents learn to solve problems. So I take abstraction to be the process by which agents can form simple abstractions simple models that still facilitate effective decision making. So if you're out in the woods trying to get back to your campsite, you might only pay attention to kind of the relevant landmarks around you, like the location of a bridge or a waterfall or mountainside, and not pay attention to things like the exact number of clouds in the sky or trees around you. But the existence of this particular abstract model raises a really natural and deep question, which is basically, where does this abstraction come from? Where do good abstractions come from, and how can intelligent agents learn them through interaction with their environment? So this has been the guiding question of my research, and this is the question that we'll look at today, where I take intelligent agents to mean agents that are effective at reinforcement learning. I take abstract understanding to mean these two classes of abstractions, state and action abstraction. And I take worlds to be a particular class of possible worlds, namely Markov decision processes, which we'll define shortly. We'll also spend some time at the beginning clarifying what is meant by the right abstraction, because I don't think it's apparent what it means for an abstraction to be a good one up front. OK, so with that, I'm just going to provide a quick high-level overview of reinforcement learning for those that might not have seen it before. At a high level, we're going to be studying the interaction of agents and their environments. For a concrete example, let's take a look at chess. So to systematize the study of chess, we'll define the class of environments of interest as Markov decision processes, or an MDP. An MDP consists of 5 components. That is, the first is a set of states. This is just the number of the way the world can be configured, so the different configurations of realizable states of the chessboard. A is the action space. These are just the things that are available to the agent at any particular point in time. What can a particular agent do in chess? The third component is the reward function that effectively describes the task being solved. So this is a function R that just maps a state and action into some real number. So in chess, you might get +1 when you checkmate your opponent and -1 when you get checkmated. The fourth component is a transition function that just describes the causal rules of the environment. It says, given you're in this state, you execute some action, what is the distribution of next states that you go to? And the final component is a discount factor. This is just a real number between 0 and 1 that expresses a relative preference between near-term rewards versus long-term rewards. So coming back to this traditional reinforcement learning loop, defining this interaction of agent and world, we can replace this world with just some particular choice of Markov decision process, which is really an assignment of those two components, a reward function and transition function. The goal of these agents that interact with these MDPs is to maximize their long-term expected reward. That is, they're looking for some mapping from state to action that achieves the most reward possible. To make that concrete, we'll talk about policies in terms of these functions, just a mapping from states to actions. We'll evaluate a policy according to the value function. So this is just the immediate reward you would get if you applied this policy in some state, plus the long-term expected reward you would get if you continued acting according to that policy thereafter. We'll also define the action value function in a similar way that just says if you act according to this policy, what immediate reward you get, plus how much long-term reward you get if you acted according to that policy thereafter. And lastly, we'll define the optimal value function, Q function, and policy in terms of V star, Q star, and pi star. So that's all the RL background I'll go into. Any questions about this so far? All right, excellent. So with that on the table, let's dive into abstraction. So the first class of abstraction we'll study are state abstractions. So here we're looking at a particular MDP represented as a graph. The agent starts in the bottom right corner and just has to navigate to the top row. A state abstraction is just a mechanism for compressing the state space of this problem. So we might induce this problem represented on the right. We can imagine this is roughly a hallway, a long, narrow hallway that we're trying to get out of. And roughly, by applying this state abstraction, we're just ignoring our x coordinate in this problem. We only care about making forward progress. We don't really care where we are horizontally. And in particular, a property we'll care a lot about is that when we solve this problem as though we're in this abstracted version, we'll end up with a policy, pi phi star, that roughly solves our original problem. That is to say, we don't throw away our ability to solve the problem that we care about. So that's one property we'll really care about with an abstraction. To be a little more concrete, we'll define a state abstraction in terms of this function that maps states in the original state space of the MDP into some new, more well-behaved state space S phi. So we'll refer to this as the ground state space and the abstract state space S phi. I just want to highlight this is building on a long and very exciting line of work dating back to the early 70s with Fox and Witt looking at approximations of dynamic programs. It's also worth noting that the ground state space could be continuous, and this new abstract state space could be discrete. That is, we're just discretizing the space in some way, or it could be that we're going from a large ground state space to a much smaller one. So the reason that we like state abstraction is that with a smaller state space, we can basically get away with more computation and less data. That is to say, the computational complexity of planning in MDPs is known to depend on the size of the state space, and the sample complexity or regret of reinforcement learning is known to depend on the size of the state space. So with a smaller state space that preserves the same essential characteristics, we can get away with better planning and faster learning. So any questions about state abstraction so far? Everyone's feeling good about state abstraction. Okay, excellent. So then the second class of abstractions we'll talk about are those of action abstractions. We'll again consider a grid world represented as this graph, but now the agent has to navigate through this little doorway shown in orange. By applying an action abstraction, we add new actions to the action space that just change what kinds of behaviors are available. So for instance, here we've added two new kinds of behaviors. The first says go directly from this blue state to this doorway, and then the second says go from this orange state up to these goals in the top row. And again, we'll like to preserve this property that says if we act as though we're in this abstracted problem, we can still come up with a policy that basically solves our original problem. To be concrete, we'll talk about things in terms of the options framework introduced by Sutton, Prekup, and Singh. An option is just one particular high-level behavior. So this is consists of three components: a start condition, end condition, and a policy. So in the example we just looked at, we added two options, the first of which took the agent from this blue state out to this orange state, and the second of which took the agent from this orange state out to this green state. So when any learning algorithm occupies the blue state, it basically has three actions available. It can either go up, left, or it can choose to execute this option, or it will act until it gets to this orange state and then terminates, where the action is determined by the policy. Yeah, like.
So I guess not to be a stickler about terminology, but I usually think of option as temporal abstraction rather than action abstraction. Because
yes.
Action abstraction might be something, the analogy to the state abstraction might be, again, something like maybe I have a continuous controller and I'm just discretizing the action space into some discrete action.
Yes, absolutely. Yeah, so there are a lot of terms to describe things in this space, like temporal abstraction, skills, macro operators, macro actions. I use the term action abstraction to encompass all of those effectively. Yeah, but it's definitely a fair point. The reason being roughly that with options, you can also express things that aren't temporally abstract necessarily. They could terminate after one time step, but I do hear your point. Yeah. Any other questions about action abstraction so far? All right, excellent. So again, building on this long and very exciting line of work, we'll define an action abstraction as just any extension to our primitive action space A with some set of options. We're just adding some new set of high-level behaviors to the agent. We could also consider the case where we get rid of the primitive actions and just study the options, but for the duration of the talk, we'll mostly assume that we're extending the action set. So if we return to this classical reinforcement learning loop where we have an agent interacting with this MDP, we can now just make a slight modification and stick these two abstractions into this mix. So now anytime the agent receives a state from the environment, it's first abstracted into this new abstract state space. And then when the agent makes a decision, it's choosing from among its available options. So the analogy with our little forest example is roughly that there is some ground state space presented by the world, but we're first going to turn it into this abstract representation. The agent's going to do its learning based on that abstract representation and then choose an option from amongst its available high-level behaviors like walk over to the bridge, walk to the west side of the forest. And then this pi-o is going to do the grounding of translating that option into some particular low-level behavior.
And what is that dotted line from the MDP through the state pathway all the way back to the option space represent?
Absolutely, yeah, that's a great point. So in order for that pi-o to get grounded, it needs to observe the ground state of the environment. So this is to say that the agent's decision-making is going to be made independent of that state. But in order for the option to actually translate into low-level behavior, it needs to know the current state of the environment. So there's an alternate, sorry, go for it.
Could it also be based off of the abstraction instead?
It definitely could, absolutely, yeah. So there could in principle be dotted lines from phi or s phi over to pi-o as well. For the purposes of the talk, we'll assume that pi-o is a function of the ground state space. But yeah, that's a great point. Any other questions here?
So I guess just to kind of debug my own understanding, like one paradigm I've sometimes seen is, so if you expect that maybe for the purposes of good exploration or something, you can effectively do some amount of planning in an abstract state space, but then really when you get down to computing an actual policy, you do want to allow it to have access to the complex observed state, so because the reward function might still depend on it in all kinds of strange ways. And so would that sort of paradigm where you're maybe like your learning algorithm is initially doing its exploration in some abstract state space, but then it still tries to build out a policy that takes the original state as input and acts based on it. Would that be permissible in this architecture?
Right. Yeah, this is a really good point. So the way in which a ground policy is implemented by this structure is roughly to define the agent as inhabiting everything below my hand. That is to say, it takes as input a state and a reward like before, and it outputs an action like before. So this whole thing is still a behavioral policy that's learning over time. This is kind of peeking into that box and saying we're going to assume this particular decomposition. And the reason I've gone for this mode is that this agent can now just be an arbitrary RL algorithm, and it doesn't need to know that it's dealing with some abstract space.
Now in this, the agent only has access to S5.
Exactly.
Okay.
Exactly, yeah. So here we'll be studying what impact does phi and choice of options have on the RL process when the RL process is sort of unaware of the fact that it's going to be using these abstractions. There are cases where those two things need to be intertwined, absolutely. Yeah, any other questions here? Okay, so as promised, the first question that we should set out to answer is what constitutes a desirable or a good abstraction? In this work, we advocate for three different things, the first of which is that the abstractions themselves are easy to construct or discover. That is, they don't take unreasonable computational or statistical budgets. The second of which is that they support efficient RL. So with these abstractions, learning is faster than without. And the third of which is that they preserve solution quality. So this is that property we alluded to before that said, you don't throw away your ability to solve a problem when using these abstractions. You want to hang on to some notion of a good solution. It doesn't have to be a perfect solution, but it should be good enough. So I tend to think about these three properties as defining constraints on abstraction space. Roughly, this Venn diagram is showing us the case where we're satisfying different combinations of these properties. So in these outer regions, we're thinking of all the abstractions that just satisfy one property. So for instance, those that are easy to construct, ultimately not that interesting precisely because it's very easy to construct bad abstractions. We can just come up with ones uniformly at random. They're very likely to be bad because they don't satisfy these other two properties. In these middle regions, we get those that are satisfying two of the properties, which start to get a little more interesting. But ultimately, if we're not satisfying our kind of computational constraints or statistical constraints, we'll be left with something where we could just set up an optimization problem where we look for abstractions that simultaneously satisfy these two things, but is ultimately extremely hard to compute. So really what I'm gesturing at here is that there's this middle region that simultaneously satisfies all three properties that really defines the space of interesting abstraction. So that's what it's going to mean to be a desirable abstraction. As one caveat, I've pitched these as Boolean properties, but none of these are really Boolean. They all come in degrees. And so really there's a simplex here that we're going to be moving around in. And I'm arguing that what we should be looking for are those abstractions that allow for the flexible trade-off between each of these three properties, depending on available resources or how critical the decision is that we want to make. So with that in mind, we can revisit the central question that I laid out before with this additional knowledge of what it means to find the right abstraction. That is, those that let us trade off between these three different properties. Okay, so with that all in mind, today I'm going to talk about two different projects that look for abstractions that trade off between these three different properties. The first of which looks for state abstractions, and the second of which looks for action abstractions or options. So to dive into state abstraction, the main question we're going to study here is looking at the trade-off made by a state abstraction between how much it compresses a given MDP and how good the best policy that can be represented in this abstract space is. So returning to our forest example, if an agent were to just use the exact state representation offered by the environment, we would end up with no compression because it's still the same state representation offered by the environment, but we could represent basically any policy that we might want, or any Q function, any value function, any transition model, precisely because we haven't changed anything about the state space. Because we haven't induced any compression, all of the kind of computations that we want to carry out on our model are going to be prohibitively expensive, potentially. On the other extreme, if we compress so that all that's represented by this agent is, am I east or west of this river, we've now thrown away the agent's ability to solve most of the problems it might care about, unless it only cares about being on the east or west of the river. So really what's going on here is we'd like to find abstractions that kind of delicately trade off between these two extremes, perhaps again depending on the demands placed on us by a particular problem or how crucial the decision is. If we really need a high value policy, maybe we'd be closer to the left. So that's what we're going to set out to do. We're going to try and answer this question of, can we find state abstractions that allow us to basically flexibly trade off between these two extremes? And when we say representing good policies, just to highlight, this comes back to this notion of preserving solution quality we laid out before. That is, this abstract policy still basically solves the original problem if we just apply it directly. It's worth noting this also applies to multitask or lifelong learning. That is, if there's a distribution of environments, we'd still like the same state abstraction to let us solve all problems in that distribution. So to get a handle on how state abstractions can trade off between compression and value, we'll turn to rate-distortion theory, which comes from the rich language of information theory for looking at how compression and distortion can trade off with one another. So the setup here assumes we have some information generating source defined by this probability mass function P of x. We're going to sample some element from this distribution x, pass it through an encoder to some latent code, that's x phi, and then decode x phi to x tilde that's supposed to look as much like x as possible. So the goal of this is to recreate x tilde just based on x phi so that x tilde looks an awful lot like x. So for another example, if we were to draw an element from this distribution, we might get this image. This is my dog Barley. We pass this image through the encoder to get some set of bits. This is just applying a PNG or JPEG compression to get a set of bits that represent the image. And then we'd like there to be a decoder that decodes these bits into some reconstruction of this original image. So the question of rate distortion theory is twofold. The first is, how similar are these two images? Well, that's defined by some distortion metric d. And the second question is, what is the rate, or how much compression is induced here, which is measured by how many bits there are in your code. So imagine for a second there's only a single bit in the code That means we can basically represent one half of this distribution as 0 and the other half as 1. And then using either 0 and 1, the decoder has to try and reconstruct every image in this distribution. But as you get more bits, you can start to pick up on more distinctions in your distribution and start to capture more of what's going on in this PMF. You have a question, Oleg? No? OK. However, note that this distortion metric D is on images. And it's kind of potentially unnatural to think about a proper metric in image space precisely because pixel-wise similarity isn't always the right thing to do. If I just inverted all the pixels of this image of the dog, it's not clear that that would be more dissimilar from what's currently presented. And so we'll come back to this in a moment to try and move away from some notion of a distortion metric. The seminal result of rate-distortion theory shows that there's a lower bound trading off between rate and distortion that says if you want a code that distorts no more than this amount, you just need this many bits in your code. You just can't get away from that fact. And then there's this Pareto frontier that basically defines what does it look like to achieve the optimal trade-off between rate and distortion. Because imagine our code was somewhere out here. We could compress more by moving down, or we could distort less by moving to the left. So roughly, we really want our coders, our coding algorithms, to live along this curve somewhere, depending, again, on the application. And just to draw a parallel to the forest example from before, when we're distorting maximally, that's when we end up with this highly abstracted representation. And when we're compressing minimally and distorting not at all, that's when we end up with this kind of full, gory detail representation. OK, any questions here?
What are your thoughts about sort of like the trade-off for nature interaction between like noise and structure in that version? Because I can arbitrarily boost as much information in my data as I want by just adding noise. And so then sort of the nature of this particular curve is sort of dependent on whether or not the type of information I'm willing to compress is fundamentally noisy or useful.
Right. Yeah, absolutely. This is a great question. So this comes back in part to this distortion metric being a well-chosen metric in some sense, that it picks up on what constitutes relevant information. And we'll come back to that in a moment. But I agree with you that that is a limitation of the framework at the moment. Any other questions here? OK, so recall that we're trying to find coding algorithms that live along this curve. In 1972, Blahut and Arimoto separately came up with a solution to finding such coding algorithms. They framed it as this constrained optimization problem, where we're basically searching for coders, px tilde x, that delicately balance between these trade-off of rate and distortion, where rate, this is the mutual information of this random variable defined by our information generating source, and then x tilde is the random variable defined by the reconstructed the reconstruction. Beta here is a Lagrange multiplier. It's just some non-negative number expressing a relative preference between rate and distortion. So if beta is 0, then this optimization problem is just minimize mutual information. But as beta grows, we start to care about distortion as well. And so it roughly carves out this curve. The solution to this problem is called the Blahut-Arimoto algorithm. And it's just a two-step iterative algorithm. It's a lot like expectation maximization that just iteratively updates each of these two components until convergence. And it's guaranteed in finite time to find a global optimum, meaning an exact point along that curve for a given choice of beta. So as we vary beta, we're going to move along that line. And this algorithm gives us a way to find exactly that coder. However, per the point made a moment ago, we have this notion of a distortion metric even baked into the algorithm. And as we think about things like behavior in the context of RL, it's not so clear that we can come up with the right distortion metric that's going to capture the nuances of what we want here. And so in 1999, Tishby, Pereira, and Bialik came up with the information bottleneck method, which extends rate distortion theory to the case of prediction. And so now we have this additional relevance variable here that's effectively going to replace our distortion metric by instead saying, given the code, can I predict something of relevance about the original signal rather than reconstruct it in its entirety? So coming back to the example of my dog, we sample this image of the dog, we encode it into some number of bits, and then our predictor just has to predict some questions about it. Like, is this a picture of a dog? It's just doing classification over here using those bits. And if it can do this effectively, we'll say that it's preserved the relevant information. And so, of course, now we've kicked the can down the road from the distortion metric to a relevance variable, but the claim is that defining questions that make sense to answer is a little bit easier than defining a full metric over this space. And so now if we just wave our hands a little bit, we'll come back to MDPs and to reinforcement learning. We have an information generating source that's just defined as some distribution over the state space. Our encoder is our state abstraction function. This is going to turn this ground state into some abstract state S phi. And then our agent is the predictor. It has to predict what good behavior looks like given only this abstract state. And then our relevance variable is going to be defined by some reference policy. We'll here call it an expert policy, but it could really be anything. It could be the agent from a previous iteration of learning. So then the premise is, given this state, I'm going to turn it into some smaller compressed state space such that any of those abstract states are still sufficient for being able to answer questions like, should I go up or down in this little hallway? So to get a handle on how to find state abstractions in the same way that the Blahut-Arimoto algorithm comes up with coding algorithms, we form the following objective. This is derived almost entirely from the Blahut-Arimoto algorithm. It still has these two components, the first of which is the size of this abstract state space. So we are assuming it's a discrete space, but I'll talk about a continuous extension shortly. And then the second component is just this notion of preserving solution quality. That is, how well can this abstract state space represent the behavior expressed by this reference policy pi e. We again have beta, which is this non-negative Lagrange multiplier that's going to express this relative preference between compression and distortion. So again, imagine beta is 0. We'd be looking for a phi that makes S phi as small as possible. So we just end up with a size 1 abstract state. And then as beta grows, we start to care more and more about distortion. So
why is this adequate? Like if I guarantee that I preserve values under the state distribution generated by pi e, but I completely bungle them on the state distribution of pi star, shouldn't that be a problem?
Yes, absolutely. So in this version, this is a problem. I will present a high-level version of a result that generalizes to the full state space based on finite samples from pi e. But I agree with you in general that it's a problem.
Well, even if you have, having finite samples from pi e is not going to help you if there are states, for instance, that pi star visits that pi e does not even visit.
Right. So if there's distribution mismatch between what states you're going to end up in, absolutely. So I agree, and I, in follow-up work, have studied exactly this question, and we've come up with a method to handle that effectively. Yeah. So in order to solve this optimization problem, it's closely related to some very hard optimization problems. And so we relate it to a version of the information bottleneck method. So the main result of this work is this upper bound coming from this is the deterministic information bottleneck. And so roughly using this upper bound.
Sorry, what is the space for optimization here? So S is some potentially continuous space. So am I looking at like all possible mappings from that original state space to some set of a fixed size, or I'm just not understanding what is the sort of mappings phi that is being searched over.
So in this version, phi is a mapping from the original state space to any possible to a distribution over any smaller state space size.
Okay.
So it could be down to 1 state, it could be to 2 states, all the way up to the size of the original state space. The only thing.
Are you assuming that both are discrete, or?
In this version, we assume both are discrete. In the subsequent version, we won't make that assumption, but.
Okay, so then it's no surprise that your optimization problem is hard.
Yes, exactly. Yes, so in light of the difficulty of this optimization problem, we take advantage of this relationship to the deterministic information bottleneck. And what that allows us to do is just minimize this upper bound. So we're minimizing an upper bound on our objective. And we don't, in general, this bound can be vacuous. Like the gap can be vacuous, but in most cases, it tends not to be. These are like very extreme pathological cases where that's true.
Can you remind us what rho is?
Oh, yes, absolutely. So rho in both cases is a steady state distribution induced by a policy. So rho e is the steady state distribution induced by that expert policy pi e. And then rho phi is the steady state distribution induced by the state abstraction and the abstract policy, the best abstract policy pi phi.
And H is entropy?
H is entropy, exactly. Yeah, and then dKl is KL divergence. And then these C1, C2 are just constants that depend on the problem size. Okay, so the takeaway here is that we have, in light of this upper bound, we can use the deterministic information bottleneck to construct state abstractions that are going to be making this trade-off between how much they compress and how much value they preserve. So now we'll walk through, yeah, hold on.
Hey, so pi-e is a fixed reference policy that is not dependent on the phi, the mapping. Right?
Yes, exactly. Yeah. We have played with versions where pi-e can evolve over time to treat it as the last 10 episodes of this algorithm's policy or something like that. So we have some results in that case as well, but for now we assume it's fixed.
So
exactly.
Is the upper bound, are the two terms in the upper bound individually upper bounding the two terms in the original objective, or right? You have two terms in the objective, and then you have two in the upper bound, and I just want to understand, is that
Yes.
the sum of the two upper bounding sum of the two, or are they individually upper bounding?
So we relate this term with this term and this term with this term, exactly. Yeah.
So I guess intuitively I'm missing how entropy can upper bound S phi, because entropy is going to be upper bounded by log of S phi. So I'm just missing something.
Yeah, we can talk about this result offline if you'd like, definitely. Yeah, there's a few nuances to that, yeah. Yeah, sure.
So I'm still trying to understand what you're actually optimizing over. So pi-e is like reference pi that is already there. That's not like optimizable, right?
Yes.
Then how do you decide on a pi star of phi? So for each phi, there's a pi star, a different one, right? Then do you optimize over that?
So we are just optimizing over phi, but phi does. Excuse me. Oh, I'm supposed to be repeating questions into the mic. I apologize for not doing that. So the question was, what are we optimizing over phi and pi phi, or just phi? Is that fair?
Yeah.
So the optimization is just over phi, but that does implicitly define an optimal policy in that abstract state space pi phi star.
Which also requires you to optimize over.
Yes. Yes. But the search space is really over phi, and then you do some check in the optimization to see, is this phi star, pi phi star sufficient? Yeah.
Right, so you could, like what you're saying is you could effectively write it as a min-max problem where you have min over phi and max over pi with v pi or something.
Sure, yeah. And the star is kind of implicit, but yeah, that's a great point, definitely. Okay, so with this on the table, I'll just jump to some results. So we'll start with a nice simple grid world. So here we're looking at the agents in the blue, trying to get to this star. And on the left, we're looking at results that show the trade-off made by state abstractions found by this algorithm, with the x-axis being these beta values. So again, as beta is 0, that means we're compressing a lot. All we care about is compression. And then as beta grows, we start to care more and more about value. The y-axis is the value of the best policy representable in this abstract state space. And so this is averaged over 1,000 runs of this algorithm. Our algorithm is shown in blue. The red is just a slight variation of the algorithm that tends to be a little bit slower. And then green is showing the value of the original expert policy. So roughly the thing to note is that when beta is 0, we compress far too much and can't represent a good policy. But then as beta grows, we start to find better and better policies until ultimately we can represent things that are about on par with that original reference policy. So that's roughly what we set out to do. And this result at least demonstrates in this simple case that that's what we find. For a quick...
So is pi-e optimal in the original MDP?
It is not. So pi-e is it's epsilon optimal. It's like...
Could you just go back to the previous slide for a moment?
To...
The previous... Yes.
This one.
So here you're allowing yourself the possibility of improving upon the expert, right? According to... Or I guess not the second bound anymore. Because you're...
So reward doesn't show up here. Right. And so as a result, there's not... it's not going to get information to improve on the expert, but we will. The extension does study this case. Right. So for a quick look at one of the state abstractions found, we'll here just color this grid world according to which abstract states each cell belongs to. So this, when beta is 0.75, we find an abstract state space consisting of 4 states. There's the blue, green, orange, and beige that roughly correspond to the pi star irrelevance abstraction that says when you're in green, going up is a reasonable thing to do. When you're in orange, going right is a reasonable thing to do, and so on.
So how do you get these labels for the different states?
So this is one candidate abstraction that comes out of a run of this algorithm. So every time we run the algorithm, the output is a state abstraction. And then this is just assigning colors to each of the abstract states found by the state abstraction. They don't all look like this.
What's the intuition for the two blue clusters to be grouped together?
Which ones?
So I'm just curious. Blue is kind of spatially quite distributed, and is it clear that the right action to take in all of them is the same, or?
Right. So coming back to your points about fixing that stationary distribution, row E, this is really optimizing for only spending bits on cases that are likely to occur under the expert's policy. And so as a result, if orange is the go right state, then it's unlikely the agent will ever occupy this top left room. And so those blue states are roughly a wash. The other thing is that the policy representable here in this abstract space can be stochastic. And so as a result, it could be in blue, half the time you should go left, half the time up, something like that. Yeah. Yeah, sure.
I'm slightly curious how you actually solved that optimization problem earlier. Phi is going to be in like the set of all the possible functions. So, just roughly the process from that to solving for this. How do you actually solve the optimization problem?
Yeah, for sure. So this comes from this mixture of the information bottleneck and then the deterministic information bottleneck from Strauss and Schwab, which was in 2016. And the premise follows a very similar iterative process to Blahut-Arimoto, where you continuously update basically the best abstract policy and the best state abstraction you've seen so far by looking at data from the expert policy by sampling from the states that occur with high probability in row E. So you visit a state, you take a sample from what the expert does. Based on what that expert does, then you say, does my abstract state let me predict that well? If it doesn't, then I need to shift my state abstraction a little bit. And it kind of toggles back and forth in this expectation maximization-like way. But it's primarily building on the existing work of the Strauss and Schwab and Tishby, Pereira, and Bialik. The main insight here is connecting the dots between state abstraction and those frameworks. Yeah. Any other questions? Yeah, sure.
So in order for you to update, I presume in the end you get a training algorithm that's iteratively updates phi, right?
Yes, exactly.
For each update of phi, I guess it requires you to approximately solve a Bellman equation to get pi phi. Am I correct?
So pi phi is updated online as well without a Bellman equation. Because there's no reward in the mix at the moment. This is purely based on trying to reconstruct expert behavior. And so we sort of short circuit that by just saying, all we're trying to do is predict what this expert does rather than care about the full value function.
Okay, but you still need to get some pi phi. Then pi phi is defined to be the optimal solution that best kind of approximates the expert pi e. Without looking at the reward, just looking at the
expert's actions. Exactly. Yeah. So it's this iterative update based on the expert's actions rather than reward transitions and so on. Yeah. We did look at an extension that played with the full Bellman equation. It's tricky. Yeah, exactly. Yeah. So just one other note on this slide is that this same algorithm also works in this multitask or kind of lifelong continual setting where we have a variety of different tasks. So this is just a same version of this grid world where now we have 4 different goals. White cells are not abstracted. They're treated as their original cell. And then anything colored is grouped together apart from these walls. So this is just to say the same framework is pretty flexible and can be adapted to a lot of different settings. So next up, we'll look at some learning experiments. So the premise here is to construct this state abstraction offline before any learning takes place. So we're going to run this optimization algorithm, output a state abstraction, and then we're going to contrast how Q-learning, this very simple algorithm, does, given different state abstractions output by this algorithm. So we'll first start with this 4 rooms domain, this little grid world we looked at. The x-axis here is number of episodes, so just number of samples the agent has experienced so far. And then the y-axis is the cumulative reward received by the algorithm. The baseline algorithm is this green line shown at the right. And then the 4 other variants are just using the state abstraction found by our algorithm with different settings of beta. So first let's look at the gray and light blue lines shown in the bottom. So these are cases when beta is very close to 0. And so as a result, it compresses the state space far too much, and Q-learning can never find a reasonable behavioral policy. These 2 up top in red and blue are cases when beta is much larger, and so as a result, it still has the expressivity to discover a good behavioral policy because its state space is just a richer representation. So this is really what we were hoping for, that we could compress and still find a good policy, but this isn't the whole story. Yeah, sure.
Just to confirm, you said that the state abstraction was learned given an expert policy?
Yes, right, exactly. So we do compute that offline after seeing some expert behavior, definitely.
There's no fine-tuning of that abstraction in this process?
No, it's fixed,
Okay.
exactly, yeah.
I was
Yeah,
curious if you thought it would make sense to compare to some off-policy methods that might also be able to make use of that data that you're going in?
Definitely, yeah. I think there's a good question about how well is a state abstraction absorbing the knowledge of an expert as opposed to some other things.
Right.
I haven't done that. I would love to see that. Definitely, I think it's a great idea.
Is there I mean, I know you have this beta parameter here 10 indicating how much compression is happening, but did you go back and say, okay, well, this indicates this much information is in the state space to say, because just by beta itself, like I don't really have a clear understanding about whether or not any information has been washed out.
Yeah, sure. So another version of this plot looks at a typically called just like a rate distortion curve that shows how does the abstract state space size vary with value. And I can say that the original problem had around 70 to 80 states, and most of both of these betas that have reasonable performance here end up with between 10 and 20 states, something like that on average. But it is a pretty high variance process. Like the abstraction we come up with does vary quite a lot depending on how you initialize and things like that. I should mention this plot is not the full story. So here is the same set of results, but now we're zooming out. We just run the experiments again. And so now what we find is that Q-learning ultimately overtakes the performance of either of these because it has that original state space with which it can represent Q functions and policies. So eventually it's going to find a better policy. But critically, red was the state abstraction with the highest beta, then blue, then these ones down at the bottom. And so roughly what I'm claiming here is that as we interpolate beta from 0 down at the bottom to beta being arbitrarily large, we can fill out the space between in the ultimate value of the policies that these learning algorithms will discover. And the ever critical first 100 or 200 or so episodes, of course this is a grid world, but the premise is that we're going to be making this trade-off between how good is our ultimate solution and how quickly can we find one, because the space of functions we're searching through is smaller effectively.
So David, we're getting a remote question, which is for your optimization problem, maybe one kind of trivial solution to think about is an abstraction that simply maps S to pi E of S.
Yes.
And do you know in your experiments if basically that's the abstraction you discover? Do you outperform that abstraction, or how do you compare to that baseline?
Yeah, absolutely. So if there's folks at a different remote location, I'll repeat the question that says, roughly, there's a simple abstraction that just turns every ground state into an abstract state for which the expert does the same thing. So group all the states together that go up, group all the states together that go left, and so on, the pi star relevance abstraction. And how does our approach compare to that? Is it just discovering those? This is a great question, and in this context, we do find that at least for highly compressing abstractions, that is roughly the state abstraction that emerges, but it's not always the case. I will say that the main qualitative way in which these differ is that as the state space does get larger, the learning problem does fundamentally change. So there are cases where just reducing to the pi star irrelevance abstraction makes learning prohibitively difficult, precisely because a lot of states end up getting grouped together. You have all these discontinuous groups of abstract states, as we saw in the example I showed before. And there are ways in which the learning problem does change when you're given basically that abstraction as opposed to something else. And so in some sense, this by toggling beta a little bit, allows us to...
So is it because the entropy term will favor other abstractions, I guess, that you might... Because for the K divergence term, that abstraction is always good enough.
Right.
I see. So if I guess the entropy part were still the original S phi, then it seems like you're pretty doomed to not outperform that abstraction mostly, right?
Yeah, definitely. So I think that
if I had like S phi plus K divergence, then it seems like I should just always discover pi E of S as my abstraction.
Right.
Yes, it can be further compressed.
Sure.
I guess no, it cannot be further compressed. So, yeah. So it seems like maybe I need to understand how the S phi term goes to entropy a little bit better.
Okay.
Because otherwise, seems like the solution might be always degenerate.
So broadly, it's a fair solution given the objective that we've defined, that you want to compress as much as possible while still preserving good solutions. I think more generally, instead of just preserving one good solution, we'd want the policy class to just be rich enough to express a lot of good policies, especially those that make discovering good policies easy, even if they themselves are not ideal. I can't claim that this objective in particular makes that learning trajectory of policies, makes that important. It doesn't put any pressure on that. But
I agree with the spirit. I'm just trying to ground it in terms of the specific objective.
Sure. Yeah, that makes sense. So I agree. I think broadly with the objective we have, this degenerate solution is a totally valid thing that we haven't yet ruled out. As learning efficiency starts to come into play, then we'll start to see some nuance enter the picture regarding like why we might not want that one, which I'll talk about shortly now as we move to continuous states. Although I don't have too much here, but I'm more than happy to talk about the details of this section offline.
Just one quick question.
Yeah,
so,
sure.
In the previous experiments, the useful information is kind of driven into the abstraction through the expert policy.
Right.
Do you have any other experiments in this where you're looking at other sort of ground truth variables to drive these things?
Yes. I don't have them in the talk, but I have looked at things like by simulation, like criteria, like making sure you can predict the next abstract state and reward, predict value, kind of other signals that are more readily available in RL.
So in that case, that's similar to what they're doing in U0, right, where they're predicting like those types of things. But what about the other types of useful facts about the world, for instance? The number, in the grid world, the number of what is it called, like the blocks you can't go into versus,
sure.
Or, you can think of a whole bunch of different interesting sort of ways to sort of extract out like useful labels from the state spaces themselves and use
definitely.
That signal. I know that people are doing that in robotics, for instance.
Mm-hmm.
It'd be interesting to sort of like compare those sorts of approaches to learning abstractions to the ones that are driven by an expert policy.
Yeah, I definitely agree with you. The reason we ended up sticking with an expert policy throughout the analysis is that it fixes that state distribution, which makes a lot of things very simple. But of course, in the more general case, that state distribution is going to be evolving as the algorithm updates its behavioral policy and explores a little bit. But I did conduct a good series of experiments kind of looking at other kinds of signal to inject into the state abstraction, and most of them work pretty well. Yeah. So in this continuous state extension, we'll just move away from the previous objective a tiny bit. Again, I'm not going to go into too much detail here, but I'm happy to talk offline about this. In this experiment, we'll look at this puddle world domain. This is a continuous grid world. The agent just gets an x and a y that are just real numbers, and then its movement has some Gaussian noise added to it. We're again going to compute some state abstraction offline. It's very similar to the previous objective, the same kind of general spirit. We have an expert policy. We absorb that information into a state abstraction and then use it to learn. The experiments are shown on the right. The results are illustrating the same general trend that on the x-axis we have time, y-axis we have performance. Here we're just comparing, again, tabular Q-learning with a linear function approximator that just uses the original feature representation, which is x and y. And so there's no reason to think that this has this admits a linear representation. And so this is not intended to be a serious competitor to this approach. It's just to say that kind of another default thing to try doesn't really work here. But again, using tabular Q-learning, we do get very sample efficient learning in this continuous state domain. We've looked at a case where we only see the expert in 3 of the 4 goals. So now each of these is one of 4 possible goals that we can sample uniformly. And then using that, we get to see some number of samples from the expert, learn a state abstraction, and then we're going to give the learned state abstraction to this agent for this 4th goal. And so here are the results for that. Again, we're going to compare linear Q-learning with Q-learning using this state abstraction. And again, this is on a held-out goal, but it's still roughly a symmetric problem. This is averaged over a bunch of runs, and so the held-out goal changes depending on the run. Still within about 10, 20, 30 episodes, we find that tabular Q-learning can find a suitable state abstraction. And just for a quick visual of what that looks like, here is the color coding indicating the abstract states. So this is where the kind of pi-e-like abstraction starts to feel potentially insufficient, just in the sense that we have multiple goals to solve, and so we need our abstract states to draw distinctions across different tasks, rather than just within the one task we care about.
So then how did you get PE? So if linear Q-learning doesn't work, then how did you get PE for this case?
So this was actually hand-coded.
Oh, okay.
The expert here was myself playing with Puddle Worlds and writing down rules for solving this. Yeah. It was actually easier to do that than get most deep RL algorithms to solve this thing. Yeah, any other questions here? Okay, I'll just quickly mention the main result from this section is on a kind of a generalization error style bound that uses the Rademacher complexity of this state abstraction class, and then tells us roughly how many samples from the expert we need before we can guarantee this closeness of the best abstract policy to the optimal policy. This again, we have to make some assumptions about how we're sampling states. That has to be fixed, but under that assumption, we can guarantee that this learned state abstraction is going to have this property.
What's delta?
What is delta? So it's a high probability guarantee.
No, capital delta.
Capital delta. Oh, yeah, let's talk about this offline. Yeah. It's basically just an estimation error, approximation error, decomposition. And yeah, there's some irreducible error here. Yeah. Okay. So next up, we're going to extend this continuous state algorithm to this, the richest setting that we've studied, which is this game Lunar Lander. Lunar Lander is a fun little game where you have this purple car that can thrust in 3 different directions, left, right, and down. The state space is 8 continuous state variables, representing things like the x and y location, the angular velocity, and so on. And its objective is to land in between these flags. It also gets a little bit of shaped reward as it gets right above the flags, and then it loses a bunch of points anytime it crashes. And as you can see, the landscape changes every time.
Is the action space still discrete?
The action space is discrete, yes. Great point. So we're going to apply the same general premise where we look at a few versions of Lunar Lander. We gather some samples, come up with a state abstraction, and give it to tabular Q-learning. I just want to highlight this was joint work with my lab mate, Kaveh Shahzadi. So here we're going to look at every 5th episode of tabular Q-learning with this learned state abstraction. And this is actually on a held-out version of Lunar Lander that's slightly different from any that we saw during test time. In this case, it just slowly hovers down. It actually doesn't get there in this one, but.
So how is pi e defined here?
So pi e, we train a DQN on this game for a while, and then we change some aspects of the environment, and then present the new version. Yeah. And it decides to settle back down. There we go. Okay. So for some more quantitative experiments, we're going to again compare these 4 different approaches. The one with the learned state abstraction, as you'd expect, is the one that's learning quite efficiently early on. Then we look at 3 different variations of representation learning for this case. Probably the most interesting is this DQN coding, which just takes the features from DQN and gives it to Q-learning. We also use tile coding that we tune for this problem, and then bucket coding, which is really just discretizing the continuous state variables. But But the takeaway here, at least in these sets of problems we looked at, is that in not too many samples, we can come up with a very simple learning algorithm and a very simple representation that can solve some pretty challenging tasks.
So Q-learning, DQ encoding is using linear Q-learning or tabular Q-learning?
Tabular Q-learning, but we did find that linear Q-learning also struggled.
I see.
Yeah.
Because, I mean, in principle, it should be much more amenable to linear than tabular.
Yes, agreed, definitely. For the purposes of this plot, we want to make sure the learning algorithm was the same, but we did do that comparison as well, and the result was pretty similar. The learning curve is a little bit more generous to linear Q-learning, but it still takes quite a while. Yeah, sure.
That's right. So if DQN works, now why doesn't the features of DQN give you some good result?
So this version of Lunar Lander doesn't have any shaped reward, so it only gets positive reward when you land or when you crash.
Yeah.
And DQN actually can't solve that.
Then how did you get pi e?
So we got pi e from solving the shaped one with some other variables changed. We learned the state abstraction there, and then we give the state abstraction in this non-shaped slight variant. Yeah.
But the DQ encoding is also using the shaped rewards. So you're using the shaped rewards, and then you're using the state abstractions
Yes.
without the shaped rewards, right?
Yes, exactly.
Okay.
Yeah.
No, DQN, the Q-learning with DQ encoding curve is not using the shaped rewards.
So
So the features were learned using shaped rewards.
That's fine.
yes,
Yeah.
yes, exactly.
But then, yeah, while
Yeah.
But the actual learning is
they were taken out.
Okay.
yes, exactly. Yeah.
Otherwise, that'd be pretty damning.
Yes, that's something would be
Yes.
fun.
Yes. Definitely. Okay, so just to conclude this section on state abstraction, we set out to answer this question of can we find these good state abstractions that are both making this new state space tractable while still representing good policies? The answer is yes, but I just want to flag that my personal view is that state space size really isn't the full story. That's not really the only thing we should expect out of a state space. It should support a lot of other things, and just minimizing the size of the state space, coming back to Aлек's question or the question from the cloud on whether pi e is the right kind of thing to preserve, there's probably more to the story, like making things easy to learn rather than just represent. Okay. So next up, we're going to talk through action abstraction. I just want to highlight this was led by my collaborator, Yuj and I. So in this context, just recall, since we've been talking about state abstraction, let's just quickly cover options again. Options were these three condition entities that define these high-level behaviors. So if the agent is in that bottom right state, it chooses to execute the option. It will follow that option policy until it reaches the orange state and then terminate, and then it makes another decision. The main question we're going to study here is to try and find options that make planning as fast as possible. That is, we're going to look to add these high-level behaviors such that this part of the process is as efficient as possible. So that's the main question of this section. To make this concrete, we'll define the planning problem in terms of the value planning problem, which says we want an epsilon optimal value function everywhere in the state space. So there's a lot of versions of planning. This is just one choice. So it's important to note that the results I'll present are restricted to this choice of the planning problem. Similarly, we'll define the speed of planning as the number of iterations needed by value iteration in order to converge. So this is, again, just one choice of the speed of planning. There are many others. We completely ignore Monte Carlo style approaches, for instance, and we ignore the branching factor. But subject to these assumptions, we're going to analyze this question. Just for a quick refresher on value iteration, suppose we have this 4-state MDP, where you get +1 reward by getting to the goal. Suppose we initialize our value function to be 0 everywhere. By iterative updates, we just propagate this reward according to our gamma, and then we converge, and we're done. The reason adding options can make value iteration more efficient is that we get these long horizon edges that just propagate information more quickly. And so as a result, if we initialize our value function to be 0 everywhere, we can effectively converge in just a single iteration. So this is sort of the promise of options here. The value iteration algorithm with options is effectively identical. This was part of the elegance of the original set and pre-cup sync paper, is that we can just seamlessly incorporate options into planning, where our max is now just taken over the actions and the options that are available in any given state. And then these reward and transition functions are just defined by the multi-type model, which is again just this kind of temporal extension of the traditional reward and transition models. And so value iteration with options just means continuing to apply our standard Bellman backups until convergence. Okay, so that's the question. Does the setup make sense to everyone?
So is it fair to still think about, if I consider two different option sets, then the cost of an iteration of value iteration might be different because I have to compute these temporally extended operators in the case of options, right? So if I have one option set which induces very temporally extended options, one which just has primitive actions, then just doing one step of value iteration would require me more time in the case with long options, right?
Right.
And so is it fair to compare iterations without taking the per iteration complexity into account?
Yeah, this is a really good point. This problem we will assume, let me repeat the question. So the question is it fair to assume that studying options that minimize the number of iterations of value iteration is really fair if we're not also paying attention to like how costly it is to come up with the transition model and reward function for the option. Is that fair? Yeah. Yeah, really great point. In this formulation, we'll assume we're given the option models as well up front. So we're ignoring the difficulty of computing those models. But I should note I have done some separate analysis on studying option models and how hard it is to come up with them. And I've proposed a model that it's equally, you need the same sample budget no matter how far into the future you need to look, and they'll be sufficiently accurate, roughly. And happy to talk about that more offline as well. But yeah, that's definitely a good point. Okay, any other questions about the setup? Okay, so the main results of this work is that in general, this problem is NP hard, maybe not so surprising. The thing that is surprising is that it's also really hard to approximate. So this is a lower bound on the hardness of approximation. And we have an approximation algorithm that roughly matches this lower bound. But even then, it's still harder to come up with this approximation than it is just to solve the MDP without options. So we view this, because this is a lower bound, we take this to be pretty concrete evidence that finding options for the problem that you want to solve, if you only need to solve that problem once, you should just solve the problem. Don't worry about finding the options. Again, subject to these caveats that what we're really looking for is things that minimize number of iterations. We're not looking at number of rollouts, branching factor, how hard the option models come up with, things like that. As a corollary, the same result also holds for distributions. So we were optimistic going into this that perhaps we could come up with options for some tasks and then use them downstream. It's hard to get away from this difficulty, though. Just for some qualitative comparisons, I'll next show results from the options found by the optimal algorithm that is solving this NP hard problem, and then the approximation algorithm, that's polynomial time. So here we'll look at 4 rooms, again this grid world, but now the goal is in the bottom right. And we're going to restrict ourselves to a particular class of options, namely those that only have a single state that initiates and a single state that terminates. And so in light of that, one candidate option that was found to be optimal was this one for speeding up planning across the entire state space. In the approximation, we find this one.
Oh, and the computational hardness still holds, right? If you have only single.
Yes. Yes, exactly. So in the k equals 2 case, so I forgot to mention this, k is indicating how many options we're looking for. So part of the optimization problem is we have a hard constraint on the number of options you can find that minimize value iterations as much as possible. So in this case, we'll look for 2 options. I encourage you just to think for a minute where you might think those option landmarks will be placed to speed up planning as much as possible. And there isn't necessarily a unique solution, but OK, so here's the optimal one. And then the approximation, qualitatively, looks maybe somewhat similar. I also just want to highlight 2 other forms of options that try to optimize for slightly different properties. So the betweenness centrality options in particular from Szymczak and Bartow find these doorways, which is just very satisfying. They solve a separate NP-hard problem that's not as focused on planning, but rather exploration. And then the eigenoptions is more about exploration, trying to reach disparate parts of the state space. For some more quantitative evaluation, here we're just looking at the difference in overall number of iterations required as a function of number of options between the optimal shown in blue and the orange is the approximation algorithm. And roughly what we find is that the two, at least in this problem, find options that are of similar quality. And so part of the takeaway here is that perhaps this hardness result is just about the worst case and not, it's only for these pathological problems. Yeah, sure.
Sorry. So are you going to tell us how to get the approximate one?
Oh, I don't have that too much in the talk, but it's based on the approximation algorithm for set cover.
Where is this your work or someone else's?
So there's existing work that comes up with a hardness of approximation for set cover, and then we adapt it to this problem. So we just prove a reduction that relates this work to set cover.
So I guess philosophically, one thing I'm still kind of unsure about. So, okay, when I think about the work of Sensek and Barto, at least I understand that maybe you have to solve a difficult problem once, but because it's kind of just about the environmental dynamics, I can, once I have these options, maybe plug in many different reward functions, and then all my maybe subsequent computations will be faster as a result. Now, speed of planning is great, but speed of planning is a pretty dependent function both on the dynamics and rewards. And so, what do I do once I have the options that would benefit from the presence of options is not so obvious to me.
Okay. So, I mean, the hope is that if you need to plan in that problem or potentially nearby problems, planning gets faster as a result of having these. Like you can do an initial upfront cost,
right,
and then.
But it seems like, anyways, the finding the options is going to be more challenging than planning, regardless.
Yes.
So, is there any way and because it's dependent both on dynamics and rewards, I can't even talk about like changing then the reward in the problem or something to use these options downstream. So I'm just sort of really lost on what this might be good for.
I see. So part of this, I would say, is that these are mostly to be interpreted as negative results that say we shouldn't be looking for options that make planning faster, which was a previous objective within the community. So this is saying that this problem is really hard, and that if you want to find options that make planning faster, you should be aware of the fact that you could just solve the MDP instead of doing that. That being said, I think there is some wiggle room around the approximation result that says roughly in non-pathological problems, it might be feasible to use this in a practical way. But I think there's more room to explore there.
So in the non-pathological cases, do you actually compare the full cost of here's the computation involved in searching for the options plus planning with the options compared to just planning without the options, or do you just
not
planning with and without the options?
Not experimentally, but the bound will say that still this approximation algorithm should take longer than just planning and finding a solution.
No, I'm saying in the non-pathological cases where you're maybe hoping to show some promise empirically, are you comparing the full computational cost of here is the cost of computing the option plus using it, or are you just comparing the cost of using the option versus not using the option?
So we're comparing the optimal algorithm versus the approximation algorithm. But we don't compare those with their upfront cost of solving the problem with just planning. Okay. I think that would be an interesting thing to study. My suspicion is in most problems, the approximation algorithm is going to be at best on par with good planning algorithms. But okay, any other questions here? All right, so in the interest of time, I will head on to the next section. So roughly, to summarize, we set out to try and formalize this question of, can we find this appropriate set of options that make planning fast? We said yes, but it takes a lot of computational work, and so this is, again, to be interpreted potentially more as a negative result than as a positive result. So bubbling back up, I talked mostly about state abstraction, a little bit about action abstraction, but I've recently done some work that kind of connects these two, and this has been a long objective in the field to try and understand how these two things relate to one another. So for just a reminder of that, we're going to be both abstracting states and choosing amongst these abstract options. The way that works in terms of this grid we looked at before is that we apply some state aggregation and we add some options that kind of have to coordinate with the chosen abstract state space. And then again, this property we'll be interested in is to say, are there ways of doing this that allow us to discover near optimal policies? So the main theorem from this work says there are broad classes of families that combine state abstractions with options that are sort of based on those state abstractions that can, in fact, preserve the representation of good policies. These classes roughly parallel existing classes of state aggregation functions from prior literature, just extended to the case where options are in the mix as well. The results I'm most excited about in this work is that we can also repeatedly apply these abstractions to come up with hierarchical abstractions that just can be of arbitrary depth d, such that, again, we preserve this property. That is, for an arbitrary MDP, arbitrary finite MDP, these classes of state action abstractions can be combined together many times to construct these hierarchies that are guaranteed to preserve value just as a function of the depth of the hierarchy. And then there's an approximation parameter in the class as well. Any questions about this? I haven't presented too many details here, so I'm mostly putting this out here to talk offline if folks are interested. Yeah, sure.
So is it true that adding options to the action space doesn't change B star?
So in this case, we're looking at removing the primitive actions and replacing it with a set of options.
I see.
And so as a result, we can only represent whatever policies are representable by the option. Yeah, it's a great question, though. Yeah, any other questions here? Okay, so with that, I will start to conclude. So I just want to highlight that most of the work I've talked about today has been on abstraction in the context of RL, and this is where most of my work has lied. I've also been interested in a lot of other spaces, including some recent work on human cognition with some cognitive scientists, some work in multitask learning and planning. I did some applied work on computational sustainability, where we made this little bandit-based solar panel prototype that was on the roof of Brown's computer science department, moving around for a while, trying to absorb as much energy as it could. And I've also dabbled in some philosophy of AI, things like ethics of AI, as well as some recent work on bounded rationality and the role that abstraction can play in that space. Really broadly, my agenda tends to fit kind of right in the middle of theory and practice, with this guiding question that I alluded to at the beginning of trying to systematize problem solving in the context of observation and action rather than symbol manipulation. And just to give a quick sense of some projects I have in mind, on the theory side, I'm interested in investigating this question of RL hardness. So a lot of abstraction is about making problems easier, but I think to give a proper answer, a proper theory of abstraction, we need to know what it means to make a problem easier. So we looked a lot at this grid world, and of course there's a lot of excitement around Minecraft. And on the upper extreme of problem difficulty, we have things like cooperative cooking challenges. And we have this intuitive sense of what constitutes the learning difficulty of these problems. But I think to get a proper theory of abstraction, we need to have a really concrete notion of what constitutes a hard learning problem. So that's a major direction that I'm interested in going and drawing from insights from, again, complexity theory and learning theory. On the applied side, in the interest of time, I'll skip through some of this. But on the applied side, I would love to take some of these ideas and try to deploy them on just simple robots like a turtlebot to see if we can scale some of the ideas we looked at before to get them to actually work on a physical system, as well as continue this line of work in computational sustainability, bringing the tools of RL and ML to bear on challenges of relevance to the world. So with that, I want to extend a huge thank you to all of my advisors, especially Michael Lippman, my advisor, who's been awesome to work with, and all of my collaborators. And with that, we'll conclude. Thank you.
The second half of the target means adding the number of actions. So how should I understand abstraction?
Yeah, so I would say this comes from, there's the kind of long lineage of work on abstraction in AI. And really broadly, it's just about transforming one problem into another problem, with the typical assumption that the new transformed problem is simpler. Oh, so I haven't been doing this. I apologize, folks online. The question was, what does the term abstraction mean if the first half we're talking about reducing the state space size, and the second half we're talking about adding actions. They seem to be semantically different operations. So why abstraction? So this is roughly coming from this lineage of work that looks at abstraction as a transformation of a problem from something complex into something simple. And that transformation can have several different meanings. It could mean compressing the state space. It could mean factorizing the state space, making it smooth, things like that. Yeah. But I agree with you. There are other terms one could use, sure. Yeah. Any other questions? Okay.
Just
yeah, sure.
pretty general question. And actually, this comes from a place that I don't understand like the depth of this literature very well, but I've seen that a lot of the classical work on abstractions, people apply to like four-room domain that you show, and usually it's kind of a single task context, right? So arguably, like maybe I want to learn some kind of abstractions so that it could be useful for some other downstream task. So are you aware of like other works that people have tried to use this idea to apply to like either multitask setting or I guess more broadly speaking like some sort of generalization notion in RL? Is that something that people have been looking at? Or?
Yeah, I would say the classical work, some classical work was explicitly interested in some notion of a domain that defines some diversity of tasks. So something even like using strips and padiddle to define a space of operators and behaviors. And then an abstraction is the thing that works well in that domain in general. So something like Minecraft. So I would say certainly the classical work in the space tried, at least on the planning side, tried to address some of that. In RL, absolutely a lot of it's been focused on things like grid worlds. There are questions of interest looking at transfer and multitask learning and continual learning and these sorts of notions. I tried to flag a few here, but I should mention a lot of the results I presented do also apply as we go from one task to a family of related tasks. But I think that's a case where there's more open questions than answered ones, definitely. Yeah, thanks. Cool. Anything else?
No,
All right, thanks, folks.